We will be talking about the number of divisors of a natural number. Okay, in order to do so, let's start with three natural numbers that are not 0 and d and x, such that d times x equals n, so d and x are divisors, positive divisors of n. Okay, in a previous video, we mentioned the fundamental theorem of arithmetic that allows us to write any natural number in a unique way as product of various different prime numbers to various powers. So we can do so for n, d, and x. Okay, so we get these slightly more complicated ways of expressing n, d, and x. Okay, now if we use these ways of expressing n, d, and x, we can rewrite the equality d times x equals n like so. Okay, and that is true because in here this is just our d, this is just our x, and this is our n. Okay, so now this is a bit more complicated, but it allows us to work a little bit with it. Okay, and here's what I mean with that. So the various d's are different from each other. The various x's are different from each other. But what happens is we can, in theory, we can combine, if for example d1 is equal to x1, okay, over to this left-hand side of this equality, we're going to have d1 to the power of beta 1 plus x plus gamma 1. Okay, so fact is that even if we combine the various d's that are equal to the various x's, the powers at which the various d's appear over to the left-hand side of this equality will only go up. Okay, so two things actually happen. Okay, d's, for example, won't go away. Okay, and what that means is that even when we combine the various d's with the various x's, these will stay here. And if we do that combination between the d's that are equal to x's, then what we get over to the left-hand side is we get a prime factor decomposition of a number. What number is it? Well, it's the number that we have over to the right-hand side. So, and we know that the fundamental theorem of arithmetic tells us that the prime factor decomposition is unique, meaning that the d's that appear over to the left-hand side have to be equal to some p's from over to the right-hand side. Okay, and what that tells us is that the prime a factor of n cannot introduce new prime factors. Again, we said that the d's have to be found among the p's, so a divisor of n does not introduce new prime factors. Also, if some of the d's, for example, if d1 is equal to x1, okay, then the actual power at which d1 appears over to the left-hand side is beta 1 plus gamma 1. So these don't go away, and even more, their powers could increase. All right, so what that allows, those two observations allow us to do the following. We can write d as p1 to the power, let's say, delta 1 times p2 to the power of delta 2 times all the way times pk to the power of delta k. Okay, now I'm not saying that this is the prime factor decomposition of d, because it could be the case that some of these gammas are 0. So we have some restrictions on these gammas. So we can say 0 less or than equal to, on these deltas, then delta 1, and is less or than equal to alpha 1. Okay, because we realize that the powers at which these, the various d's appear in here, cannot be greater than the corresponding powers of p's, right? Also, we have 0 less or than equal to delta 2 less or than equal to alpha 2. Okay, so this is the condition we have on delta 2. And finally, on delta k, we have the condition 0 is less or than equal to delta k less or than equal to alpha k. All right, so we can write d in this shape subject to these conditions. Okay, so now we can notice the following, that if we want various divisors of our number n, okay, all we have to do is we have to pick various deltas here subject to these restrictions. Okay, so then we can conclude that the number of divisors of n, okay, is obtained like so. Okay, so the gammas, the deltas are, delta 1 is in between 0 and alpha 1, including 0 and including alpha 1. So for delta 1 we have alpha 1 plus 1 many options. Okay, for delta 2 it goes from 0 including 0 to alpha 2 including alpha 2. So for it we have alpha 2 plus 1 many options. Okay, and so on. And for delta k, it goes from 0 to alpha k, including 0 and including alpha k. So we have alpha k plus 1 many options. And just because of the fact that we have the freedom to pick our deltas subject to these conditions, our basic counting technique, which is called the multiplicative principle, tells us that we can choose this family of deltas in these many ways. So we can just multiply alpha 1 plus 1 times alpha 2 plus 1 times alpha k plus 1, and this is the number of divisors of the number n.